So we have to understand some of these terminologies in order for us to continue on with circular motion. So period of motion and frequency of motion is something that we're going to be talking about today. All right? So what does this language mean? When we talk about the period of motion, okay, the amount of time it takes for an object to go around once or complete one revolution. All right? So the unit for period is in seconds, and it is represented with capital T. So that capital T is definitely different than lowercase t. So, period of motion, amount of time or amount of seconds it takes for an object to complete one revolution. Now the frequency of a motion is the reciprocal of the period, or the number of revolutions per second. So if it spins like 2 revolutions in 1 second, your frequency will be 2 revolutions per second, right? It doesn't always have to be a complete revolution. It could be a fraction of a revolution. You could only turn maybe, let's say, half a turn per second, then your frequency would be half of revolutions per second, or half per second. So frequency represents the number of revolutions per second, right? Or per second, or simply hertz. Now if you take a look at the lights on the ceiling right now, it may seem they're constantly on. But believe it or not, those lights are blinking 60 hertz, which means it is blinking 60 times in 1 second. So it looks like it's constantly on because your eyes cannot tell the difference. You know, when you go see a motion picture, you know, they're going at 25 frames per second. So even though it's still frames, 25 hertz, it looks like it's in motion because it's moving faster than your eye can perceive or receive the information. All right? So it's very, very important to understand the difference between period and frequency and how they're related. All right. Let's take a look at an example. So if we know an object makes 6 revolutions in 2 seconds, my frequency will be 6 revolutions in 2 seconds, or simply 3 revolutions per second, or otherwise known as 3 hertz. Okay? Now, time needed to complete one revolution is simply just the reciprocal of that. So, in order to complete one revolution, it only takes 1/3 of a second to complete one revolution because it makes 3 revolutions in 1 second. So the period would be 1/3 of a second. All right? So period is the reciprocal of frequency, and frequency is the reciprocal of the period. All right? And since an object travels the distance of 2 pi r, which is the circumference, when it's going around in a circle, right? We can calculate the speed of an object going in a circle by doing distance divided by time, but the distance is the circumference, which is 2 pi r, and the time that it takes to complete a circumference is known as the period. So now we can calculate the speed of a circular motion with 2 pi r over the period t. And since frequency is 1 over t, we can represent this same as 2 pi rf. So these are the exact same things. Okay? And if we substitute this 2 pi r over the period t for v into our a radial, or centripetal acceleration, then what happens is a radial is equal to, right, 2 pi r over the period t quantity squared divided by r. So if we actually square this inside the parentheses, we get 4 pi square r square over period square, whole thing divided by r, and one of the r's at the bottom and one of the r squares gets canceled out, leaving you with the r at the top. So you don't always have to memorize this, but you can always derive this once you know this, you know? And since we know period is same thing as 1 over frequency. We can replace that 1 over period squared with just frequency squared. So this is exact same thing. Okay? So now sometimes in like AP test, I've seen it a few times where they ask you, giving you this, a radial or centripetal acceleration. They ask you, A, centripetal acceleration is A, directly proportional to radius. B, inversely proportional to radius. C, they're not proportional at all. D, I don't know. Which one would you pick? Right? You would say it would be inverse, right? But that's wrong. That would be the popular wrong answer, right? Why? Because this V has R in it. So when you square the V, you're going to have R squared. So look at this. They are directly proportional to each other. And that's usually the question you guys will pick the popular wrong answer looking at V squared over R, and you will pick inversely proportional. But they are not. They are directly proportional to each other. So make sure you understand that. I'm giving you one of the answers. Right? Yeah. Right. So what happens when things are not going at a nice constant speed, when things are going in a circular motion? So far we only learned about uniform circular motion when things were going in a constant speed. Well, if we have non-uniform circular motion, that means as it's going in a circular motion, it could be speeding up or slowing down. Okay? So, in that case, if we have anything speeding up or slowing down, what kind of acceleration do we have? Huh? Very good. That is correct. We have two kinds of accelerations. We had radial acceleration and tangential acceleration. Radial acceleration only measures things when they're going in a circular motion, right? But what happens when things are speeding up or slowing down from your summer assignment? What kind of acceleration? Tangential acceleration is the correct answer. Good. So, when we have something that is accelerating, where either speed or the magnitude of the velocity changes, then we have a linear acceleration. And that linear acceleration is tangential acceleration. And that tangential acceleration magnitude can be calculated as change in V, which is the magnitude of V, divided by change in time. Okay? So, when we have radial acceleration, the a sub c, we already know what that is, and that is basically V squared divided by R. This V is the instantaneous speed at wherever the point that you're looking at. Okay? And this delta V is basically, change in V in given amount of time, okay, if you have constant acceleration, okay? So this tangential acceleration, right, does the speeding up or slowing down of the object. The radial acceleration never speeds up or slows down an object, but it always changes the direction of the object radially inward, right? That's the centripetal. So this one, as we know, the position function of time is equal to, right, r of t, right? And that's the position function, right? Then if we take a derivative of that, r prime of t is simply v of t, right? That is the velocity function, right? And if we take a derivative of that, then we have second derivative of the position function, which is the first derivative of the velocity function, is my acceleration. Okay? So we can use this as well to figure out the tangential acceleration given the function. Okay? And if we take a third derivative, of course, of the position, that is the second derivative of the velocity function, which is the first derivative of the acceleration function, and that is jerk. Okay? But we're not going to worry about that too much, but this is mathematical, definitely a mathematical term we use when we have change in acceleration. And that can happen in nature. Matter of fact, you'll find a lot more. Nothing is ever so smooth. Very jerky. So how do we analyze when we have, circular motion, and to see what kind of accelerations we have? So analyze the tangential acceleration first. Okay? The question you should be asking, is there any, right, speeding up or slowing down? Right? So is it, right, speeding up or slowing down? If it's no, right, then, right, it's uniform circular motion. Right? Therefore, we only have AC. However, if it's yes, then it is non-uniform circular motion. Therefore, right, we have a tangential and a radial, or a sub c, same thing. All right. So if this happens, where we have both of these, then here's what you should do. Take the circle and cut it. So, cut the circle. Okay? And then open the circle up and then straighten it out. Okay? So it's like nice one straight line. Okay? So cut it and make it into a straight line. Then use the constant acceleration equations that you have to memorize to find V final with the acceleration tangential given. Most likely, it'd be a good idea to use equation number 1, which is Vf is equal to Vi plus a tangential t. And you probably also know the second equation, right? Which is delta x is equal to VIT plus 1/2 a tangential t squared. This delta x is wherever the arc length is. Okay? Because you're cutting this and you're straightening it out. So if you don't travel the complete circumference, your delta x is same thing as the arc length s. Okay? Then once you figure out your v final, right? Or sometimes you have to find your time first to figure out your v final, right? This v final can be now substituted into your a sub c equation, right? To get your a sub c, right? So now the a sub c is equal to, right? The magnitude of a sub c is equal to your v finals, right? Magnitude squared over r. Then you have to add these two acceleration vectors, right? Vectorially. So here is your a tangential, which is going to be tangent to our trajectory, and here's your a radial, which is a sub c. And when I add these two acceleration vectors, I get my resultant of a total of that. Okay? So here is my a tangential, let's say. Right? So here's my a tangential. And then I'm going to add my a radial. Right? So here's my a radial. And when I add these two, I have my resultant acceleration of a total. Okay? Well, this looks like my a total is in third quadrant, so it might not be a bad idea to look for my angle beta, my reference angle beta, to calculate my theta for the direction of my total acceleration. So my a total, right, is simply a vector addition of those two accelerations of a tangential plus a radial. So the magnitude of this a total is equal to simply square root of, right? Square root of a tangential squared plus a radial squared. Okay? Or, if you're not even sure about that, you can say that is the same thing as square root of, right? Delta v over delta t squared plus, right, v squared over r quantity squared. And we know beta is equal to tan inverse of. Now you have to be careful. Depending on where things are, my beta can be different, right? Opposite over adjacent. Therefore, opposite is AC in our case, over adjacent, which is A10. Things can change though, depending on where your beta is. And since my theta is in third quadrant, right? It is 180 degrees plus your beta, right? Because you're in third quadrant. Are we okay with that? All right. So, let me see, humor me, and see if you can show me that you understand what we did, and see if you can do the next page. I'll give you approximately 7 minutes. Right? I'll give you 7 minutes. Look, I gave you the answers, okay? So if you did it right, you should be very happy. If you can't do it, then we'll go over it. But I just want to make sure we are all on the same page and make sure you can do this page. Hint, hint. All right? Get to work. All right, so welcome back. So non-uniform circular motion example problem here. A particle moves clockwise in a circle of radius of 1 meter. All right? It starts at rest at an origin at time t is equal to 0, and it speeds up at a constant rate of 1.6 meters per second every second. So just from that, what's given to us? What do we know? We know the radius, r, is equal to simply 1.0 meters. What else? Huh? A tangential. What's my A tangential? My A tangential is 1.6 meters per second squared. And it tells us that it speeds up at constant rate of. And just by looking at this unit, you should definitely tell that is an acceleration. What else do we know? We know the initial velocity V initial at VA, right, which is 0, right, when t is equal to 0. What else do we know? It travels from A to B, which is halfway around the other side for part A. So what is the length traveled, my arc length S? Pi r. But what's my r? 1. So we know a lot of things here. So we know S is equal to simply same as delta x, because we're going to cut it open and flatten it out. That is simply pi times 1 meter, so it's pi meters. We also know that initial velocity Vi at point VA is equal to 0 meters per second. We also know A tangential, which is equal to 1.6 meters per second squared. We're looking for time, right? So here we can probably use equation number 2, where delta x is equal to VIT plus 1/2 AT squared, and this A is the A tangential. Delta x, pi meters. VI, 0, so the whole term drops out to 0, plus 1/2 times 1.6 times t squared. So t is equal to square root of simply 2 pi over 1.6. And that should come out to something like 1.98 seconds. That wasn't that bad. Now they ask, what is the speed at point B? Well, we know a lot of things. We know V initial, which is VA, is 0 meters per second. We also know A tangential, which is equal to 1.6 meters per second squared. We also know now the time it takes to go from A to B, and that is 1.98 seconds. And I'm looking for V at B. So that's simply VF is equal to VI plus AT, which is equation number 1. So VF is VB, VI is 0 plus 1.6 times, we know the time to be 1.98, therefore my V at point B is equal to 3.17 meters per second. Well, what is the direction of my V at point B? Which way is the direction?
Down.
Down. tangential to the trajectory, right? It's always, the velocity is always tangential to the trajectory. So it is down, right? So that is the direction of my velocity at point B. Or you could simply say velocity at point B is equal to negative 3.17 meters per second y hat. You can also do that. But what about centripetal acceleration at point B? What is the centripetal acceleration at point B? And which way is it? Well, to calculate the centripetal acceleration, it is simply v squared over r. But we are looking for the centripetal acceleration at point B, so we have to use the v at B squared over r. And that is equal to 3.17 squared over 1. And that comes out to 10.05 meters per second squared. But that is just the magnitude of my A sub c. So, which way is the direction of my A sub c? Towards the center, which is to the left, right? That's my A sub c's direction, right? So my A sub c can be written as negative 10.05 meters per second squared x hat. What about E? What is the tangential or linear acceleration? Oh my God, that's so hard. That was given to you, right? So A tangential, the magnitude was given to us at 1.6 meters per second squared. Well, what about the direction of this? It's speeding up. It's tangential. So which way is it? The direction of A tangential. Down. Down. A tangential. So to complete this, my A tangential can be represented as negative 1.6 meters per second squared y hat. Therefore, what is the magnitude and direction for the total acceleration? So here's my AC. Here's my A tangential. I'm adding them up, right? I could have done A tangential plus AC, same thing. And here is my A total. This angle is my reference angle beta. Again, this is in third quadrant, okay? Therefore, when I calculate my magnitude of my A total, it is simply square root of, right, 1.6 squared plus 10.05 squared, right? And if you work that out, my A total magnitude comes out to 10.18 meters per second squared. But what about the direction? The direction, you have to think about beta. Now beta is equal to tan inverse of opposite over adjacent. Well, opposite looks like A tan here, right? But this can change depending on where things are, right? Over adjacent, which is AC. Therefore, my beta is equal to tan inverse of, right, A tangential, which is negative 1.6, AC, which is negative 10.05, And if you work that out, your beta comes out to 9 degrees. And therefore, your theta, because it's in third quadrant, is 180 plus 9 degrees. So your theta is equal to 189 degrees. So that is the direction. This is the magnitude. So your A total is equal to 10.18 meters per second squared, comma, theta is equal to 189 degrees. Or if you want to put this in Cartesian form, you just simply say, right, negative 10.05 x hat minus 1.6 y hat meters per second squared. All right, I'll see you guys on Thursday.